appliances in my hands, and I'll try to make it work. It was just pointed out to me that there is a misspelling in the title, but what? Is of course on purpose. Yes, you guessed right. Well, it's before I start, I think it's great to be here back on the Tsinghua campus to see so many familiar faces, old friends, colleagues. The time I was here, I have greatly enjoyed, and I see that this center is clearly prospering in a way that I had not thought possible 15 years ago. So before I start, let me show you a picture that is not really related to my talk, but I should say, I think it was mentioned by Professor Yao. He came actually to the Netherlands, where I'm from Utrecht, actually to make a contribution to my retirement conference. And here's a picture that you can see him, and I suppose it's also perhaps new to. I have to. There you have. So what you see here is a mill which actually produces, well, planks. The input is a tree trunk, and what comes out is a plank. And as you can see, we also had some wooden shoes, befitting a great man. Okay, that's my little joke. So the subject of my talk is something it's a project that my collaborator Benson Farb and I started a couple of years ago. And the name, a Thurstonian approach to form manifolds, is something that requires a little bit of explanation. So I should tell you first what Thurston did. Thurston, by the way, was the supervisor of Benson Farb. You knew him quite well. This work of Thurston refers to the following problem. You take a closed, oriented, connected surface, so that's completely given by its genus, and then you take an orientation-preserving diffeomorphism, but what you are really given is not this diffeomorphism, but rather its isotopic class. And what you try to do is to find a optimal representative of that diffeomorphism in its isotopic class. Well, it's quite remarkable that this has a very nice answer, and that answer that was in fact given by Thurston, and I'll show you what the answer is like. So I've attempted to draw such a surface, and we suppose here that diffeomorphism, orientation preserving, as I said, is given. Then the statement is that the isotopic class of that diffeomorphism has the property that it leaves invariant it will not leave invariant a closed curve or collection of closed curves, but of course it will leave invariant their isotopic classes, because you want the property about isotopic classes. So there is a collection of those curves, sort of cutting up the surface in pieces, each piece being a surface which is the interior of a compact surface with boundary. And the assertion is then that you can find a diffeomorphism in this isotopic class that preserves this collection of curves. And then, of course, automatically some power of that diffeomorphism will preserve each connected component. So the M1, M2, and M3 in this case, and will act, that power then will act on that piece in a very simple manner. Either it will be the identity, right? I'm referring to a power of the diffeo, not the thing itself, or it will act on it in the most complicated way, namely as a pseudo-Anosov diffeo. When I say in the most complicated way is sort of, there's nothing being preserved there, but you can actually be very precise in what you mean by that. It means, I did not write this down because it's not so relevant for what's going to follow, but let me try to say it in a few words. It means that you have, on that piece of surface, you have two transversal foliations that are being preserved by that diffeo. But what's more, these foliations come with transversal measures, and that these transversal measures are not being preserved, but are sort of eigenmeasures. One measure is multiplied by a certain real number greater than one, and the other is then multiplied by its inverse. So the local model, what's happening is quite clear. It's sort of stretching in one direction, and it is sort of shrinking in the other direction. That's the picture that you have in dimension 2. It's a beautiful picture. Now, this is what we want to emulate, or what in higher dimension. Now, the first case to consider, of course, would be dimension 3. But dimension 3 is a little bit special, and that is precisely because of the work of Thurston. Thurston had this sort of geometricization program in dimension 3, and I will not explain what this program is, but the upshot of the story is that this is not going to be terribly interesting in dimension 3. So let's skip that dimension and pass on to dimension 4. In dimension 4, well, things are getting really complicated in principle. Let's therefore restrict ourselves to a situation which avoids all the complications from the fundamental group. So assume the manifold is simply connected. And then we have already some great theorems at our disposal. There is a theorem that goes back actually to, well, the 1980s, I believe. And it's a theorem which has been revisited recently by Gabay and a number of collaborators, because there were some issues with the proofs that were given then. But the theorem is a wonderful theorem. It says that if you have, it basically says that the isotopic classes, but now the topological isotopic classes of homeomorphism, so this is not the statement in the differentiable category, that these are basically given by the orthogonal group, by the group of isometries of the second homology group. The second, if you have a simpler connected form manifold, the second homology group is free abelian, but it comes with an intersection pairing. This intersection pairing is unimodular by Poincare duality. If the homeomorphism preserves orientation and it preserves the intersection pairing. And in fact, the statement is, if you have two homeos which induce the same orthogonal transformation in the H second homology, then they're isotopic. And complementary to that, every orthogonal transformation arises in this manner. So that gives you a pretty complete picture. However, I'm not interested in the topological category. I'm interested in the differentiable category. And then, of course, in dimension 4, we have this rich bag of examples that come from the theory of complex surfaces. So we're going to focus on a class of algebraic surfaces. And at this point, I should say, yeah, Benson and I, we started this program and we made the first steps. And what I'm going to do today is to describe one of these steps. The complex surfaces that we focus on are what is called the elliptic surfaces. So you're not all algebraic geometers, so I should really tell you what an elliptic surface is. So here's, yeah, there it is. This is my attempt at drawing one. It is a two-dimensional compact analytic surface, which fibers, almost fibers over a Riemann sphere. I assume here that the surface in question is simply connected. Then it will fiber over a Riemann sphere in a sense that all the fibers, almost all the fibers are genus 1 curves. So topologically, these are tori. And there are a few exceptional fibers. And since we are not going to do here algebraic geometry, but differential topology, we just assume that the singular fibers are as simple as possible, nodal fibers. And so, let me see if I do it right. So, yeah, you can see that. So here's, this is a typical fiber, right? You have here the torus, but a nodal fiber arises sort of by, this is a sausage that I've drawn here, and it is obtained by taking in the torus a circle on it. It should be an essential circle, so you don't bound the disk, and that's being contracted, and you get this picture. There's a very simple way to compute the Euler characteristic of such a surface. You do that by pretending as if the Euler characteristic is some additive with respect to fibers. Smooth fibers are tori, so they have Euler characteristic 0. So if you're going to sum over all fibers, you only get contributions for the singular ones. And so you just count the number of singular fibers, and that will give you, in fact, because every singular fiber has Euler characteristic 1, you get, in fact, the Euler characteristic of the whole surface. This is what we call a genus 1 fibration. And if the genus 1 fibration admits a section, that makes then automatically every fiber an elliptic curve rather than a genus 1 curve, then you say call it an elliptic fibration. So this is a little bit of the algebraic geometry that comes with this situation. Okay. Now, I've drawn also, as you can see, a section that is red. This is supposed to be this red thing here. Okay. Get the next slide, but doesn't seem to work this way. This way, but yeah, there it is. Okay, here's an example. I mean, this is a very basic example, a very classical one, and it arises by a pencil of cubic curves in the plane. So I've drawn in the complex plane, the projected plane, 2 cubic curves intersecting transversally in 9 points. And you can now look at all the cubic curves passing through these 9 points. That's just a 1-parameter family. If you give each of them an equation, then it's just given by a nonlinear combination, non-trivial linear combination of these equations. That gives you a 1-parameter family, parameterized, in fact, by the Riemann sphere of cubic curves passing through these 9 points. Now, they intersect transversally. That means that at every point, the tensions of these cubic curves are different. And you can easily convince yourself that if you take this 1-parameter family, that the tension directions passing through a given point can be any direction. And so what we do is we blow up these 9 points, meaning simply that we replace each point by ascension direction. And the effect of that is that these cubic curves all get separated. They are no longer meeting, they are pairwise disjoint. They fill up the whole blown up space, and they indeed give you a vibration over P1 with fibers, these cubic curves. It comes with cubic curves, as you know, have genus 1, and it comes with a section. In fact, it comes here already with 9 sections, but there are many more. This is actually a very basic example. It's the rational elliptic vibration, but all the others, at least topologically, can be sort of obtained from this one by what is called the base change. So here's an example. I have to go, I have no idea where I should direct this. Yeah, there it works. Okay, so what you do is you have this family over the Riemann sphere. Now you take a default branch cover of the Riemann sphere. D is a positive integer. And you pull back the family, and you get another family that I denoted by MD. The number of the Euler characteristic gets multiplied by D, and you find easily that its Euler characteristic is then 12D. For D is equal to 1, well, we got what we just discussed. For D is equal to 2, we get a K3 surface, which is, of course, topologically also extremely interesting. And for D greater than 2, we get surfaces of Coda dimension 1. And for these surfaces, the elliptic vibration that I described is sort of canonically given. It's given by it's the sort of canonical vibration of that surface. There's no other elliptic vibration besides the one we just obtain in this manner. Okay. Now, there's a theorem that goes back to Moiseson. It tells us that all other simply connected elliptically fibered surfaces are diffeomorphic to this one. And it has a number of properties that I have mentioned here. And they all relate basically to the second homology group of that 4 manifold. So I've denoted that second homology group. I've abbreviated it by lambda D. And it has a special element. That's the class of a fiber. That fiber has self-intersection 0 for evident reason. So it's an isotropic class. It's also an indivisible class. It's primitive. And there are these assertions that you can read, I hope. So the intersection pairing on the second homology is, of course, going to be unimodular by Poincare duality. And it's even or odd according to whether D is even or odd. And I give you, in fact, also the signature that fixes at the isomorphism type of this lattice entirely. And the second statement is then, well, we have this class of the fiber. As I said, it is an isotropic class. Its self-intersection is 0. And then we can take its perp modulo the span of that class. And that will still be unimodular, but the remarkable thing is that will be now an even lattice, and the signature will be as given over there. Now, for D greater than 2, there's a remarkable theorem, which is due to Friedman and Morgan, based on Seiberg-Witten theory, that says that the class of that fiber is a diffeomorphism invariant up to psi. So every diffeomorphism of M of the manifold onto itself will take the class of that fiber to itself or to its opposite. And so we want to exploit this when we study the Thurston approach. Take the Thurston approach to this. Let me see. A little bit of an exercise. Yeah, okay. Well, it leads us to introduce what we call the smooth Mordell-Weil group. And so what is the Mordell-Weil group in this case? A Mordell-Weil transformation is a diffeomorphism, at least for us, of such a elliptically fibered Bohr manifold that in every fiber is just a translation, right? Every fiber is not just a genus 1 curve, it is actually, it has a complex structure. So with respect to that complex structure, it becomes, in fact, an elliptic curve or principal homogeneous space of an elliptic curve. So it's well defined what the translation is, but the translation may depend in a differentiable manner on the base point. And so we get this, it's an infinite dimensional group of Mordell-Weil transformations, but what we're interested in is not the whole group, but its connected component group. And that is what I will call the smooth Mordell-Weil group. Now, the smooth Mordell-Weil group appears in our story. It's clearly an abelian group because it consists of these translations. So here are two theorems. The first one is that this smooth Mordell-Weil group is faithfully represented on the second homology group, abbreviated here by letter D. And it is realized there as what are called Eichler transformations. Doesn't matter so much what that means, but let me just say that these are the transformations that you expect to run into, namely, you take the automorphism, the orthogonal transformations of the second homology group that are unipotent and preserve the fiber class. And that is then automatically an abelian group. And that abelian group has a structure of a lattice, and the lattice is precisely the lattice that was on the previous sheet. So that is this E-perp mod the span of the fiber class. That's the first theorem. The second theorem says that the whole stabilizer of this fiber class in the second homology is realizable by diffeomorphism. Every such element is thus obtained, and that construction is based on how equinodal pairs give rise to Dane twists. I use here terminology that I did not introduce, so let me sort of give you some idea what's going on with the picture. There you go. So what is the situation here? It's looks a bit cryptic, but think of this as a disk downstairs, which is in the Riemann sphere. The disk contains 2 points over which we have a singular fiber. And in the sort of path arc that connects these 2 points, there are no singular fibers, of course. So over that arc, you have just a torus. And when you approach one of these points, that torus becomes a nodal curve. It becomes this sausage. And that means that we are going to contract a circle on that torus. And the assumption here, that's what's called equinodal, is that these 2 curves that are being contracted are in fact isotopic on the torus. And that is sort of intended to be, right? You have here that one and that one, they're clearly isotopic. And I've actually given you the isotopy here. And that one here sort of gets contracted there. That one gets contracted there. And if you look carefully, you see that this is actually a topological two-sphere. Well, it looks like a rather weird two-sphere, but in 4 dimensions, it turns out this is just a smooth two-sphere. Although it looks unlikely, but you can make it smooth at least. And what is now happening is that you can move, you can move these 2 points in the base here around each other, like a simple braid. So one goes around the other. Then you can follow that upstairs to see what's going upstairs. And then upstairs means on the 4 manifold. And the effect on the 4 manifold is a Dane twist, a 2-dimensional Dane twist with respect to that two-sphere. That's a two-sphere with self-intersection -2. And there is something like, if you know what a Dane twist is in dimension 1, you may be able to guess what it is in dimension 2. And that's exactly what's happening. And that's a rather important ingredient in the proof of the result that I mentioned. Now, let me then close with a consequence of this fact. Yeah, there you go. So it implies, given the results that I mentioned earlier, that in fact this elliptic fibration that is algebraically given, or at least a priori, is in fact a sort of diffeo invariant as well, in the sense that every diffeomorphism of M, well, we have to be a little bit careful, more careful than I was intending to state it here, that every diffeomorphism of the manifold takes the given elliptic fibration perhaps to another one, but that other one is always isotopic to the given one. So that is sort of intrinsic to the manifold structure, which is perhaps a little bit unexpected. So I began with 2 pictures. Well, let me also finish with 2 pictures. Here you go. So you see here the original Johan West building, Yao standing next to his sculpture. And well, this is not so well visible as it should be, but we have there Cheng. I think you are, what is it? We are sort of, this is at Sanya. We are sort of, and Yao, of course, in the background, there's Witten. I don't think we were doing some planting or whatever it was like. So. Happy anniversary, Yao.
We see you come back. Any questions? Yeah, coaching.
That invariance has to do with the fact that the quadratic dimension is 1.
Yeah. So it is well, it is a differentiable counterpart of the fact that the quadratic dimension is 1. So the complex fibration, elliptic fibration, is of course intrinsic to the surface, but the isotopic class is, that's basically the upshot of that result, is intrinsic to the underlying differentiable manifold. And the assumption is here, of course, I made that restriction, but I did not say perhaps explicitly that we assume that the fibration is generic, so that the only singular fibers that we have are of this very simple type, nodal fibers.
Okay, yeah, I mean, the way I understand it is that the canonical bundle is a set of fibers, basically.
Yes,
More of
yes.
it, and maybe that's why these things are preserved.
Yeah.
Okay.
Yeah.
So how's the smooth model view group related to the actual model view group?
Yeah, yeah, so that, there's a difference. Because this is, in general, a lot larger than what the actual model value group can be. Because the actual model value, the actual model value group, that can only involve the algebraic part of the homology. So all these classes are integral of type 1, and of course, that contains the fiber class. And you have, what you do is essentially you take the fiber class per mod the fiber class, and that is as big as it could possibly get. But in these cases, well, the Hodge structure is pretty non-trivial. So it's not just all of type 1. There's also, the geometric genus is positive.
So in case the actual model view group could be, let's say, of course, it could be finite.
Yes.
And your
yeah,
group is
Yeah.
still huge.
Yes, yeah.
But if I know that the model view group is, has a certain rank, can
Yeah.
you relate the ranks of the smooth?
Yeah, almost in the way I described.
Okay.
I mean, a little bit of the exception. I mean, if you do this for d is equal to 1, so rational elliptic surfaces, there's not that much difference, because the ranks will be the same in the generic case as I described. The rank will be 8, in fact.
I see.
But already for d is equal to 2, and the things change, because you have the geometric genus is 1 in that case.
Okay, right.
Yeah.
In the classical Thurston construction, he builds, like he takes these simple closed curves and 2 sets, and he builds pseudo-Nossoffs out of them. I imagine your elliptic surface could have a structure of elliptic surface in more than one way.
Mhm.
And could you then compose Dane twists, these 2-dimensional Dane twists, to get pseudo-Nossoffs?
Well, I think for d is equal to 2, it can be indeed in more than one way, and it is a situation. So that's the K3 case, and it's a case that we do not fully understand yet.
Okay.
You have, in that case, pseudo-Anosov transformations, and these were, I think, first studied by McMullen. And he has very interesting examples, because these examples are non-algebraic K3 surfaces. And so these are, if something gets non-algebraic, then it is a little bit outside our day-to-day experience with surfaces, right? It then becomes more abstract than it already is. If you go beyond that, d greater than 2, now then the upshot of my story is that there is essentially only one elliptic fibration up to isotopy.
I see. Thank you.
Other questions? Yeah.
Similar questions. In parallel to Thurston's geometrization of 3 manifold.
Yeah.
So we have 4 manifold. Now you consider case of the elliptic case, like torus. So how about this hyperbolic case? It's like a quadratic.
Are you referring to the dimension 3 case?
Yes, yeah.
Well, my understanding, I'm not an expert here, so I have to be treated carefully. But my understanding is that the geometrization problem of Thurston leads you to a kind of decomposition of the 3 manifold that's intrinsic to the 3 manifold. So every diffeomorphism will respect the diffeomorphism. And then, of course, if you have these hyperbolic pieces, these are pretty rigid, right? They don't come with that many, they don't admit big diffeo groups.
Maybe you need to delete a lot of divisors.
Sorry?
And delete a lot of divisors from 4 manifold.
Yeah, possibly. Yeah.
So other questions? Yeah.
One over there.
Yeah, in the beginning of your talk, you mentioned this is the first step in your drawing project.
Yes.
What's next? Is there any directions you think would be good for the future endeavors?
Well, I wish I could tell you in a sense. Well, I mean, the first, I did not say too much about this, but this is actually what I would regard as the four-dimensional analog of a very simple type of diffeo on a surface. I think this is something like a mix of a finite group of diffeomorphisms and Dane twists, multi-Dane twists. But of course, the actual pseudo-Anosov transformations are not in this picture yet. And it is something that we need to understand better. And so it's a project with all very good intentions, but how these intentions are going to pan out remains to be seen.
Thanks.
Evan, let me propose a simple question.
Okay,
You take the cosine of the ball,
yes,
which is very rigid.
yes.
I believe the group of diffeomorphism, the component is contractible.
Okay, that's it. That's an
It should be
interesting.
good generalization of what happens in touchment space for one
Okay.
dimension.
Okay, yeah,
Cosine of the ball is extremely rigid, as I proved, depending on the topological number, 3C2 equals C1 square.
uh-huh.
As long as there's a complex structure, it has to be cosine of the ball. Based on that, I think it should be very close to prove the statement I
Okay,
proposed.
well, that would be great, yeah, yeah.
Okay, other questions? Okay, great. Thank you very much indeed.